Okay, nice to have you all here. All seats were taken, about 100. And today I will talk about calibration. Calibration, the webinar topic is, the name of the webinar is Calibration is Not Enough, Making Better Groundwater Models. My name is Dragan. I'm working with small company Environmental Modeling Solutions. And just a little bit about me. Just a few 10 seconds, 20 seconds. I get my bachelor, master, and PhD in University of Belgrade, Earth Science Department. Currently, I'm accepted for specialization at Johns Hopkins University, Department of Environmental Engineering. I have about 25 published papers and book 2016, Mathematical Modeling of Groundwater Flow and Contaminant Transport was published. What I did mostly in actually I'm giving training in last 20 years, but intensively last 1 year. This is how it used to look like. This is with Slovenian Environmental Agency. And okay, the next picture is also very interesting. This is on civil engineering in Belgrade with John Doherty and about PEST. But more and more, I will go out from this presentation. I am doing this by online. Something like this webinar. This is my website. If you go to training, you will find a lot of courses. Of course, groundwater modeling, groundwater remediation, geological modeling, remote sensing. So, yes, and that's about introduction. So let's speak about groundwater models. So, okay, these are real models. I mean, these models are exact replica of big airplanes or choppers, and that is what we cannot do with groundwater models, because we don't know in such details, we don't know the model, the subsurface. So when people are talking about models, these are real models. We are making something like which can be called the shadow of those models. We simplify that. Usually, I will skip. Yes, I will send you later. I should do that now. I should. I will send you later. Really, one good book about groundwater modeling, and I will talk now only about calibration. What is a typical approach in last 50 years? Is zone-based approach in calibration. Okay, this is I picked from my colleague John Doherty. Very nice picture. So just to see my pointer. Okay. So just because you have always done it that way doesn't mean it's not incredibly stupid. Okay, I want to just a little bit shock you, because zone-based approach is prone to a lot of errors, although it's used in the past and people are using it in present. Okay, this is by the way, I use different programs, but most of my time in last 20 years, I am using groundwater vistas. So I really have a good experience with groundwater vistas, great technical support. And yeah, okay, let's go to subject. So this is typical zone-based approach. You see this zone, for example. This was done 20 years ago. It was my first model, 1997. So this is zone-based approach. We define zones, but what is the problem? I will jump directly to subject. It's obvious, especially if you are geologists or hydrogeologists, that we don't know the shape of these zones. And the other problem is that we set it up before calibration. So on that way, we are introducing errors which can be very hard to quantify. Very hard to quantify. So, okay, this is another. This is what is typically done with calibration. And now it's the question. There is some other, that will be a topic for next webinar. It's highly parameterized inversion with regularization. I know that it sounds not so nice, but pilot points in PEST are such technique, and that's considered the, let's say, updated, better version compared to this zone-based approach. Okay, now let's see. This example was done by a student of John Doherty, the author of PEST, and the question is, how wrong can a calibrated model be? First, I will show you example from his student, and then I will show you my example from the field. Okay, this is model grid. Dimensions are 500 meters times 800 meters. This is northern boundary and constant head on south boundary. We are releasing a particle. It's here. And we generate stochastically a hydraulic conductivity field. So we pretend that we know exactly the subsurface, which is actually not true, but in this case, we generate it artificially. So we are following the time particle need to go and exit here. So this is reality, let's say reality. These are groundwater heads, for example, here. And let's see if we start with one zone and with pilot points, what is going on with calibration with different number of observation points. So true time is 3,256 days, and exit point is existing 206 meters. So we have 84 head observations. That's really a lot. I'm sorry. So then we have a case with 42 head observations, then 24, then 18, 12, and okay, so let's see how the model and pilot points are calibrating the model. So exit time, exit point. So we are tracking particle from here, going this way. Okay, let's see. When we have 84 observations, no noise. So you see the error of calibration. So this is true, and this is what we got by calibrating 84 observation wells, and this is what we got hydraulic conductivity field. So this is not a zone-based approach, this is pilot points. Highly parameterized inversion with regularization. When we have less observation, it's even worse. So you see the difference between true and calibrated prediction, I mean. 24, more errors. 18 observation, more errors. 12 observation, you see the difference, it's 2 times. So I just want to remind you the title of this presentation. How can we be wrong with calibration? So calibration is not enough, that's the point. We need uncertainty analysis. So the solution, we need to move into the field of uncertainty analysis of our groundwater and other models. Now I'm going to show you a case study. So this was done first time in 1997. Dimensions are, this is about 10 kilometers. It's alluvium in Southeast Europe. This is 10 kilometers, and again, this is 10 kilometers approximately. Okay, let's erase this. Okay, on the right side, we have a river. It's this. On the left side, we have edge of alluvium. This is inflow from the south. This is outflow from the north. So here is the cross section. This is approximately, I think, about 12 meters. And the thickness of aquifer is 10 meters. So this is two-dimensional case. Let's erase this. So we have a model, 10 kilometers times 10 kilometers, thickness of aquifer is 10 meters, but the aquifer is really good hydraulic conductivity. And the question was how much water we can get by wells from this area. Okay. So as I told you, this was first done in 1997. I revisit in coming years, 15 years, I revisit this model several times with more and more data and more sophisticated calibration and prediction, uncertainty prediction models. Okay, this is a grid. I should change this slide. It's not so nice. Okay, this was in natural state groundwater heads. These rectangles are wells. And as you see, this is direction of groundwater flow. So based on a calibrated model, okay, I got 270 liters per second that can be used by wells in this region. It was a long time ago, as I told you. But, whoops, sorry. So, several years ago, I did the pilot points. What are pilot points? It's the way of highly parameterized inversion with regularization. It can be with or without, better with. And these are the, just a moment. If you have any questions, just let me know, or I will try to answer it later when I finish this presentation. Okay, these are pilot points. I will show you that live later. And with pilot points, I calibrate the model, and this is what I got. So you see, this is what I got by manual calibration, and this is what I got from from pilot points. Okay, this is not a perfect. You see, this is called bullseyes, which means that it's artificial high hydraulic conductivities. It's only here, a little bit here, but it's pretty good. What is interesting, you see this blue color. It is the zone of low hydraulic conductivity. Hydraulic conductivities are here. So it's low. And what is interesting, PEST, I'm using, of course, PEST with the pilot points, automatically derive these zones. So we are not giving, like in this case, we are not giving zones ahead, but we are giving it during the calibration and based on our calibration target or monitoring well observations. And what is interesting, I want to emphasize this. You see, PEST found it by itself, this zone is of lower hydraulic conductivity. And you see, I did that 20 years ago, but I knew that this zone is of lower approximately, because we have aquifer testing here, aquifer testing here, aquifer testing here, and we knew that it's lower conductivity. This is the value. So what is interesting is that, Actually, PEST and pilot points, whoops, not yet, derive this blue zone by itself, which I think it's pretty good. I didn't see, maybe there exists, I didn't read every article, but it's very rare to find this comparison. But okay, we were talking about a little bit calibration, but now the topic, calibration is not enough. Where is the catch? The catch is that even with pilot points, you have non-uniqueness. Non-uniqueness is the term, it's the one of the main problems in groundwater modeling, and you have different, you get the same result with different parameters. So in this case, uncertainty analysis with null space Monte Carlo was done, and basically you are generating realization which are then calibrated, and in this case I will show you 10 equally calibrated models. So you see, this is one realization. First, let's say. This is second, all are calibrated well. This is third. Fourth, okay, I will not write anymore. Fifth, 7, 8, 9, 10. And all of these models are calibrated. And for each of these calibrated model, I run the prediction. And this is where we are coming with decision making. Better models, better decision making. Just a moment. Based on this uncertainty analysis with PEST, capacity of proposed groundwater source range from 190 liters per second to 320 liters per second. So I tried to simplify this, but I mean, you have plenty. We can on my courses or other courses, it can be covered in several days. But I think that you got the point. The point is that with equally calibrated model, 10 equally calibrated model, we get huge difference in groundwater source capacity in prediction. So this is why I said this. This is why I called this this presentation webinar. Calibration is not enough. We need to go to uncertainty analysis. Okay. Okay, I have one question. Okay, how you define equally calibrated model? Yeah, that's a good question. I will answer it right. Which means that for calibration, you have some statistics, let's say, and reasonable of results. So both statistic of calibration and reasonable of results are the same for these 10 models. So I hope that I answer your question. So if you have any question, I was trying to keep this. Okay, why is not? Okay. I will wait for a minute or 2 or 3 if you have any questions. In the meantime, I will show you that's all what I'm talking now. This is my website, training page, several, I think 10 courses, and some of them are mode flow beginners, advanced course, and what I'll show you here is taught on my online courses. So, okay, one more question. For both steady state and transient solution, no, this was only for steady state. Pilot points can be used for transient solutions, but in this case, I was using steady state. Thank you. And questions? So the next question, so what is conclusion? Which is better, zone based on pilot points? Zone based or pilot points? Definitely none of them is perfect, but in literature, state-of-art literature, pilot points are much better, much closer to truth. So we can never know the truth, but pilot points are closer, much closer than zone-based approach. So yeah, definitely pilot points are better, but not perfect. So we need to go to uncertainty analysis analysis. Okay, I get. Can we use pilot points approach for complex model that has longer running time? Yes, of course. Yes, of course. You have PEST in groundwater vistas. You have all of that. Okay, I will show you that. I will show you now, live. Yes, I almost forget that. So you see, you have PEST, PEST, PEST THP. Let's do it now. So these are, okay, questions are coming. So the answer, yes, it can be, these pilot points can be used for complex models. Okay, I will wait a few minutes more, but in the meantime, I will show you how this works in groundwater vistas. So let's run first the model. Okay, so this is all one zone, 2 times A minus 3 meters per second. Saurian units, it's old units, it's very high hydraulic conductivity. So let's run. We have options. Now create data sets. I'm nervous when I do live demonstrations because you never know what can be. Okay, we don't have errors, we don't have warnings. So I will show you. It should run now. Yes, you see, sum of square weighted residuals is 88. Now PEST will lower it. It's 80 now where my mouse, I'm moving my mouse. It's 11 now. I must tell you that I'm using very low number of pilot points just to keep it for this demonstration. You see, from 88, sum of squares of residuals are 2 now. We don't need any more. I will stop PEST. Import results. Okay, you see, 4 centimeters, 19, 1 centimeter. I'm not talking now about regularization. Regularization is very important thing, and I will cover it in next video. But let's do, so just to remind you, we start with 1 hydraulic conductivity zone, actually without zone. And now I hope that everything went well. Yes. So I will draw a little bit. I have bullseyes, that's artificial, but with regularization I can get rid of that. But again, you see, model found, just bear with me, model found this blue zone as low hydraulic conductivity zone, which is in reality. This was very simple, but I think I got your attention. We can do include aquifer testing, flow, everything, and constrain our solution. But I practically show you now the example. Okay, let's go to questions. Can a recorded video be available after the live stream? Yes, yes. So the uncertainty analysis is done with PEST in predictive mode. No, actually PEST has predictive mode. I did not use it. I just calibrated, I just made 10 equally calibrated models and then make prediction. Let's say semi-manually. I hope that answered your question. Okay, next question. How we do pilot point if kx is not equal to ky? Yeah, that is good question, actually. I'm not so sure. I think I will need to check. I know that you can calibrate ky, kx, and kz, but I'm not sure about kx and ky. I need to take a look at it. Please contact me on email. How many pilot points were used? In this example, only 17. Just a moment, I will show you. Just a moment. Okay. So here you see this 1, 2, 3, 4, 5. I don't want to count anymore. You are going to sleep. So 17, it's very low number, just for this demonstration. Okay. Do you use, next question. Do you use your conceptual understanding of different hydrogeological zones at the site to assign initial values of hydraulic conductivity to the pilot points? So in other words, some zone-based information is transferred to pilot points, at least initially. Yes, of course, we are in pilot point, we can, okay, I will show you that. Showing is better than talking. So you see, when I generate, what I give is initial value, closer to aquifer testing values or field values. We have minimum and maximum. So that's what we need to do. Pilot point initial value, minimum, and maximum. So we can adjust every single of these pilot points to match aquifer testing, for example. And I had a question, just a moment. No, I had a question ky. It seems to me that only kx and kz can be done, but I will check. I will check. So only kx and ky, but there is probably I will check. I don't want to confuse you now. Okay, pilot points are points with observation head value available. No, observation head values are different for pilot points. Pilot points are treated as parameters, and observation head values are targets. Recently, next question. Recently, I have been using hybrid approach, specifying pilot point sets in specified zones. Yeah, what do you think about? Yeah, that's good. Actually, I'm working one model in states where there are zones, and within zones you have pilot points. So yeah, that's a good approach if you know the field, subsurface, at least some geophysical exploration or whatever. Okay, next question. In the past, I have created zones from results of multiple pilot point runs, using both the special distributional values and special uncertainty to define the zones. Comment from your, okay, I need to read carefully this question. It's not so easy. Just a moment. Multiple pilot point, okay, using both. I'm afraid I'm not clear what do you mean by spatial uncertainty. So the question was, in the past, I have created zones from results of multiple pilot point runs, using both the special distributional values and special uncertainty. It's not clear for me what is special uncertainty, so if you can clarify me, or it's better to just send me an email if it's a longer story. Okay. So it seems to me that I will wait a minute or more for more questions. In the meantime, this is my website, consulting training software. And training. Yeah, in last year I'm mostly doing trading. I have some satisfied clients. So, okay, I will not mark it anymore. Okay, no more question. So I will put recording of this webinar and notify you about that. You can contact me on my email on LinkedIn. And especially for attendees of this webinar, if you are living in Europe, you can get 5% discount on Groundwater Vistas. And if you are living in North America or South America, you can get 50% discount on my online course for modeling. This is my online. Every video is pre-recorded and you can always ask me about questions. So this is, so I just want to feel you good after this presentation. Okay, one more question. What is the most critical source of uncertainty, geological or hydraulic parameters? It depends. That's why we need a model. Some kind of sensitivity analysis will be good. So geology or hydraulic parameters. We need both. Conceptual model of geology and hydraulic parameters measurements. But I need to think a little bit. Yeah, we definitely need both. But which is most critical source? I think it depends on the case. Is it possible to get presentation? Yes. Can you control the radius size of pilot points affected area? Actually, pilot points are used, just a moment. Values between pilot points are interpolated. So you have that here. No, structures. It's here. So this is where you set up a variogram, kriging options, and other things. One more question. Okay, that was the question. Okay, let's wait a minute or more to see if there is more questions. Yes, as I promised you, 35 minutes. So it wasn't long. Okay, let's wrap up this. So, okay, one more question, sorry. What is your approach to uncertainty analysis? I just show you. So I will switch it again. I'm using null space Monte Carlo in PEST, producing calibrated hydraulic conductivity fields. And then, I mean, there are other ways, but this was done in this case with PEST, I mean. And then I'm making prediction for each of these hydraulic conductivity, calibrated hydraulic conductivity fields. Okay, thank you. This is very nice. I had a lot of questions, which means that people are interested in this. Thank you. Okay, so I will inform you via email and send you the presentation, the video recording of this file. It will be probably on my website. And thank you very much. Again, this was, I get a really good feedback from you. So again, contact me if you have any question or find me on LinkedIn. I'm very active on LinkedIn. Again, thank you very much. Hope to see you soon.